Welcome to Legends of Data and AI. Each episode includes inspiring and actionable data and artificial intelligence insights from global leaders across industries. Your host, Dr. Usama Fayyad, was the first Chief Data Officer at Yahoo and is Chairman of Open Insights and Executive Director of the Institute for Experiential AI at Northeastern University.
Hello, everyone. This is Usama Fayyad. I am Director of the Institute for Experiential AI and Professor of the Practice at Northeastern University, also Chairman at Open Insights. Welcome to another episode of Legends of Data and AI. Today, we have a very special guest, Alex Vespignani, who is the Sternberg Family Distinguished Professor at Northeastern University, has appointments in the College of Science, in the College of Computer Sciences, and in the Bouvet College of Health Sciences. In addition to being a AAAS fellow and receiving honors for his great contributions in analyzing and understanding the spread of COVID-19, he is a computational epidemiologist, prior to that, a physicist, and with a long record that I'm not going to spend my time talking about. We are very honored to have you here, Alex.
Thank you for having me, Osama. It's really a pleasure to chat with you.
So let me start with a question. How did you become? You are the director of the Network Science Institute, a very well-known institute in a space that, in my opinion, is under-leveraged in AI and data. But how did you become interested in complex systems, network science, and epidemic modeling?
Well, this is because of my, I would say, quite strange pattern in science, so trajectory in science. So my PhD is in theoretical physics, and I was doing mostly research on statistical physics and material sciences. And, statistical physics and the computational modeling of materials, you handle a lot of atoms, a lot of particles, you do large-scale simulations, and underlying those systems, there is a network always. It's a network of interaction among particles, atoms, molecules. They are more regular, and at a certain point, I did start to be attracted by, how to say, networks in different areas, like, okay, the network of human contacts, how we interact, social networks on the internet. That was at the early time of the World Wide Web and the first, little Facebook graphs, etc. So this is, I got interested in, okay, let's try to understand and use the methodology that comes from physics to understand the interconnectedness of those systems. And then I slowly drifted into network science with a focus at that time on computer networks. I was working a lot on the World Wide Web and the physical internet structure that is anyway, a self-organized systems, that there is no entity overlooking the development of the internet or the web. And so they were naturally self-evolving organism, although man-made, that were, in a sense, the classic example of complex systems. I got more interested in complex systems, complex networks, and more into computer science. So I moved into a computer science department, but then when I moved there, people started to tell me, well, you do a lot of work on networks, so why you don't try to apply those ideas to how people move from one place to another and the spread of disease? And so then, again, in a certain way, by chance, prompted by other people, I started to be interested in public health. That has been my main drive for the last, at this point, 20 years. And this is why, in a sense, you can explain also why I'm in the College of Science, College of Computer Sciences, and the College of Health Sciences at the moment.
I've always the structure of large networks like the internet is fascinating, and I've seen some of your work in trying to kind of characterize that structure. But I always felt that leveraging network models in AI and machine learning has been slow and not as widespread as it should be, which is a shame because complex systems need a network representation. Why do you think this is the case?
That's a good question. There are, I think, several reasons for that. First of all, network science for a long time has been confined to small networks. The data availability was not that big. And indeed, the revolution of network science started with the availability of high throughput experiments in genomics and the internet and the World Wide Web, so availability on human behavior through mobile devices. And so that was, in a sense, network science really evolved at a very fast pace in the last 25 years. But in a way that was really to generate the foundation to try to do the phenomenology, in many cases, like really natural experiments and data acquisition. And also at that time, I think artificial intelligence and machine learning was in a moment of a little, how to say, slow a slow pace. There was not the computational resources that we have now. And again, artificial intelligence was coping with the lack of large data set, etc. So in a sense, they moved at the same time, but on parallel tracks. And what we are seeing is the convergence of the two sciences now. Now, I think really is the moment where there are a lot of low-hanging fruits that can be harvested by combining network science with artificial intelligence. And there are two ways. One is really to use artificial intelligence to understand better networks. The high dimensionality of network data is one of the main problems. And for sure, AI can really contribute immensely there. At the same time, we can use network science. And for instance, what has been done in neuroscience is to understand better artificial intelligence. And so that's really very promising directions that could bring major advances. So I'm really, I would say, very, very hopeful for the future.
That's great. Look, having been there at the start of establishing network science as a field of research, are you pleased with its evolution? Anything you would wish to see happen to make it much more widespread in use and as a philosophy of thinking about systems?
I think network science was pretty successful in the last 20 years. So it really spread like a wildfire in many disciplines. The way that we represent networks, the way we visualize networks is now a kind of state of the art. It's many of the tools that have been developed in network science, like community detection, a new way to look and characterize interconnected structure, have become usual work tools in many areas. At the same time, I think the concept of networks, the way we use networks to conceptualize the reality, is very widespread. So this is for sure. And then now also the merging with artificial intelligence and networks in artificial intelligence as really the way to understand and learn system is breaking new waves and new ground. What I would like now network science to go is to really demonstrate fully its power in solving major societal challenges. When a field is well established, and network science is well established at this point, you tend to see the research field, and many of the researchers get trapped into technical problems and things which are within the community. I think we don't have to lose sight of the big prize that is, we are going to face existential challenges in the future, from climate to inequalities, pandemics, scarcity of resources, all major migration that we see in the world. So all that we need to provide answers, and I want to see networks really trying to provide new advances and tools to face those challenges. That's what we really have to do as a community, not get into too much to talk to ourselves, but try to branch out in other disciplines and contribute to the effort that we have to do for those major challenges.
Yeah, and having been there at the start of data mining and data science myself, it continues to be one of my big frustrations to see kind of the lack of leverage of the richness that network models can provide on top of data. They are way under leveraged, and unfortunately, as we see kind of neural networks and deep learning evolve, a lot of people are trying to rediscover stuff from scratch versus trying to impose a structure on top and benefit from whatever knowledge we have. Along those lines, can you share with us some stories of any interdisciplinary collaborations you've had with researchers from other fields and how these collaborations have enriched your work?
Well, first of all, let me start by saying that really what I strongly believe at the moment is that for many challenges, for large areas of science has become a team sport. So we really need to assemble interdisciplinary teams. We really need to have different expertise altogether, different angles, point of view, and approaches, and I think this is what really is important at the moment. There, when you go like I've done, to go through different fields, you move from physics to computer science and then to health science. What for me was impressive was part of what you were mentioning. First of all, that there is a kind of recurrent rediscovery of things and by areas and with rephrasing with their own language, and every time, even at the inception of the network science field, many of the concepts you realize were discovered perhaps in mathematics, several decades ago, and then you rename them, and so I think what will happen in artificial intelligence is that we will rediscover things, and we will bend those concepts to adapt to the area. But this is good as far as it is positive and not to generate conflict of attribution or petty things among scientists. I think this is fine. What is fun is that there is really a language that is different in the way you communicate science. For me, it was very fun once. The first time I went into epidemiology, I understood the need to team up with epidemiologists to write the paper. You really go to the language. And so we wrote this fairly elaborated paper about the spreading of actually, this is many years ago, more than 10 years ago, but it was about spreading of pandemic flu and through the world. But I wrote the paper mostly like a physicist would do. So a lot of graphics, plots about the behavior of curves, etc. And then my epidemiologist collaborator sent me back a very short email saying, you have to rewrite the paper, more tables. And I was not understanding, what does it mean? Why more tables? And then you realize that, okay, this is the language. In epidemiology, you really need to see the numbers, the very small differences. In physics, you are interested to the trend, to the fact of how some behavior in the long term, and we always talk about the infinite size limit, the thermodynamic limit. In epidemiology, no. Is the attack rate 5% more bigger or smaller? It's a difference. And so it's true that papers in many cases have long tables that list all the numbers, etc. So it's really a matter of, from time to time, of simple things on the way you communicate, and you have to learn. You have to embed yourself in the community. When you do interdisciplinary work, you really need always, even if you are 60 years old, you can add all the successes in previously in your career. You have to start from scratch and be a student again. And I think this is the fun part, actually.
I love that. And I love the expression that science is now a team sport, or should be a team sport, which we know in some cases it's not. The next question on my mind is how has your work on epidemic modeling and simulations contributed to the public health response during pandemics like COVID-19?
Well, I was, as I was mentioning to you, we did start to work on pandemic preparedness, I think more than 15 years ago. At this point, I'm sorry, but I have to say 20, I'm getting old. So in a sense, for us was natural as soon as there is an health threats or emergency to contribute to what I call the intelligence work. Let me be clear here. I always say, the people who fight the battle and risk their lives are the medical doctors, nurses, all the practitioners that are in the front line when there is a health emergency. What we are trying to do on our side behind the computer screen is to provide the intelligence. So the where, when, how much, and possibly as far before as possible to help the people on the field to prepare, to plan, to manage and organize their work. For us, for the COVID-19, the work started in early January when we got the first news from China. At that point, you are really in what we call the complete fog of war. You don't know what's happening on the ground. You have just a reporting of a few cases here and there. There is not that much information. At that point, we rely on very simple approaches to provide what we call situational awareness. So the cases are 20, but they are really 20 or 20,000. And that's the big difference. And this was indeed the scary part of those early days, because after 1 week of harnessing with the data, we had estimates for the outbreak in China that was of tens of thousands of infections, and the things was obviously very large, was widespread. And the second part that we did with simulations and modeling was to try to understand the international diffusion of the virus. That was what kept us busy during February. That is called the cryptic phase of an epidemic or a pandemic. That is that stage in which you don't have infinite testing capacity. Actually, at that time, there was very limited testing capacity that was mostly used for cases with an history from China, of a travel history from China. We knew that, however, the cases were already widespread in the world, and so we were trying to map and get some information on what was the real situation on the ground in terms of transmission. That was our work in mid-February, was to call, look, although you have very few cases detected, probably very likely there is thousands of infections per day, both in the US, Europe, other places. And then we were providing the numbers and the analysis backing up those numbers in order to start the preparation of what happened then in March and April, and then all 3 years of work following that. The other things we contributed is the scenario planning. So you do simulation in which you study a lot of counterfactual. What if we do this? What if we do that? What if we close school? What if we we keep people at home, and so on and so forth. And then the last part of that is the most, how to say, tricky is the actual forecast, because scenario projections are not forecasts, are projections according to certain assumptions that you do, and generally those assumptions are prompted by your interactions with the policymakers, that what are the logistic capacities, the resources, and so on and so forth. The forecast is more short term. It's 1, 2, 3 weeks ahead, and trying to understand what is the trajectory of the disease, and that's very, very. It's tough job. We are not at the level of weather forecast for several reasons we don't have time to discuss today, but that was an effort that we carried forward for 3 years together with the Center of Disease Control, with other agencies, including the World Health Organizations and many others, to generate what we call ensemble forecasts, so that they don't rely only on a single model. There is a consensus of model. It's more state of the art, similar to what is done also in weather forecasts for large weather events like hurricanes or major snowstorms, and so on and so forth. So it was really work in many different areas of different kind. It was very operational. So this is the work that we did is what we call the wartime work, that is very different from the peacetime. The peacetime work is where you develop new theoretical approaches, new models. You think about, how can we improve the merging of mechanistic model with artificial intelligence, and so on and so forth. During wartime, you have to provide answers. So you have to put all your weaponry at work, in a way, in terms of modeling, computational tools, and the reaction times are very, very small. Many times you get a phone call and the answer is required in a few hours. And so, this is all the kind of range of work we have done during the past 3 years.
And I love the characterization, from foggy to cryptic to counterfactuals and scenarios to forecasting, and then more solid and more reliable forecasting. That's a great characterization, and it's great to have folks like you kind of working across all those phases. Let me ask you, on another dimension, in what ways has artificial intelligence and machine learning influenced or has been integrated into your research, particularly in epidemic modeling and network science?
Well, machine learning and artificial intelligence are part now of what we do in many different ways. One is for sure the use for many predictive tasks on where we have enough training data. Machine learning and other more complex artificial intelligence tools can be very, very useful. So, for instance, I can tell you, for forecast, the short-term forecast, 1 week, 2 weeks, 3 weeks ahead, where you have at that point several weeks, months, perhaps years of training data, the machine learning tends to be very hard to beat. They are a great asset, while more complex mechanistic models might provide more information. In a sense, they provide also some explanatory power about the mechanism that from time to time you don't find in machine learning, but have more issues in terms of parameterizations and assumptions, and so on and so forth. The other things is that even for the mechanistic simulations, we use machine learning in many different ways. For instance, maps we need very accurate maps of the population. That is not just where we live, but also the age stratification, et cetera, et cetera. Now, those maps are produced through machine learning that combines data, census data, but as well, for instance, the light emission from the Earth's surface captured by satellites and human mobility and so on and so forth. So machine learning is part of the creation of the data sets that we use also in models that works in a different way than machine learning. I can tell you this as an example. A few years before the pandemic, I was working on, I received a phone call because there was another health emergency, perhaps not everybody knows, that was called Zika. Zika is a vector-borne disease. Is transmitted through the bites of mosquitoes, and it was quite a major health threat, especially for during pregnancies. If you get infected, there is a lot of chance. So the risk of miscarriages and abnormalities at the birth are very high. And so, it was spreading like wildfires, especially in Latin America. And the health agencies were in contact with me, telling, well, we need large-scale modeling of this epidemic. And they say, guys, I really have a hard time now in helping you because mosquitoes do not have a cell phone. I don't know how to map the mosquitoes, how they move. And actually, I was a little bit naive because I didn't realize that, first of all, mosquitoes do not travel that much, likely enough. They stay in an area. But actually, people have been collecting data on mosquito for many, many years through the careful work of scientists that put mosquito traps. And then those data were aggregated and associated to many other indicators of geography, urbanization, population, etc., through machine learning to produce beautiful maps of mosquito abundance across the world. And those mosquito maps have been used by our model to generate projections and situational awareness on that epidemic. And so really, in that sense, machine learning was a great asset to do things that we could have not done otherwise.
Yeah, no, that's a great example. So maybe I'll combine a couple of questions in one, and watching the time. AI and machine learning, I mean, potentially, and these are just quick thoughts, can they be used to help understand or improve our understanding of complex systems and networks that you end up getting? Any weaknesses in AI that you would like to see strengthened? Any role you see for AI and machine learning in playing a role in predicting and managing future epidemic outbreaks?
Oh yeah, that's for sure. We are talking about high-dimensional data sets. We are talking about data sets which are biased, which have gaps, and machine learning could help to fill those gaps, to understand the structure of the data, to generate quickly, fast enough forecasts and predictions. One of the problems is the problem that we are always, in a sense, struggling with machine learning and artificial intelligence, and is the fact that in some cases we have these what we call tacit knowledge, by using the Polanyi thing. So the black box-ish nature of artificial intelligence that for public health intervention in some cases is not the best situation. You want to understand why things happen. And so I think a big battle is to have more understanding of machine learning and artificial intelligence results, and how to say, all efforts to open the black box and to create explainable AI is really one of the major things. So I would say that I see again a bright future of research. I think public health technology, the way we see it moving forward, it really depends on artificial intelligence, but then we need to improve the way we use artificial intelligence. And there is also a kind of awareness on the way we use artificial intelligence. We always be mindful of the limits and the biases, and in a sense, not accept whatever computational model or whatever artificial intelligence algorithm will tell us as an oracle, oh, this is it. But, I think as a tool for reasoning, as a way to look at the problem and generate answers to the questions we have.
No, that's understandability and explainability is definitely a grand challenge. How can researchers, governments, and private entities collaborate effectively to tackle global challenges like pandemics using the tools of AI, network science, and complex systems?
Well, I think what we have seen in the past years is that there was no enough training in the dialogue between people using those tools and then the policymakers and the people transferring the information generated by those tools on intervention on the ground. I think, let me give you the example. If you have weather disasters, you know that there is the National Weather Forecast Center that provides information to FEMA, to the National Guards, and then the policymakers, and everybody has a playbook that they use to face the crisis. With pandemics, we didn't have that that playbook in a way, and there was some disconnection in the communication. So policymakers were not really. Initially, they were having a hard time in understanding and trusting the information coming from the intelligence community. You see, when you have the projection of a hurricane that is hitting Florida, you have the numbers. This is math. Again, is computational models. But at the same time, you have a big photo from a satellite that shows the hurricane that is approaching. And so everybody believes what is there. When you provide, numbers about a pandemic, there is not that photo. And everybody was telling, well, but perhaps let's wait another week. Let's see really if the people are showing up in the hospital. And that is not the way to respond to a pandemic. And that's really a matter of creating a pipeline, of communications where all the tools that we have, all the science that we have is latched with the policy making and the people that will make the intervention on the ground. And so I think really there is a need to have this infrastructure and nurture this infrastructure. We need a national pandemic forecasting and center. We need a national center for research in that area. We need the national exercise and practice. And I hope we have learned the lesson. Although I'm not so hopeful, but that's where we really need to go in the future.
And those are great analogies. So in the last 2 minutes we have left in this episode, I'll ask you two quick questions. One is, can you share any ongoing or future projects you're excited about that utilize AI, network science, or complex systems to address pressing scientific or societal challenges? This is at the high level.
Yeah, so that's a very good question. So, we do, and these are projects where AI is very important. The first one is that you imagine when we do simulations and scenario projections, forecasts for epidemics, we go down to the level of single individuals, how they commute, they go on a plane, they are in contact with each other. These are large-scale simulations. That is really a challenge when you have to provide answers in a few hours. And still, even with all the supercomputing in the world, that's a challenge. We hope through artificial intelligence to bypass and circumvent some of those problems by using surrogate models that learns from a subset of our simulation and then can generate the answer that we want by that learning process without doing billions of microscopic simulations. Other things are related to, for instance, to interventions. We know that we have there is no best intervention, because there are so many dimensions. You can close schools, but you can close schools of different grades. You can keep people from working, et cetera, et cetera. So there are many, many dimensions. And so how we combine in the most appropriate way. First of all, we need to decide what is the functions that we are trying to minimize. But then, you have so many degrees of freedom that we think that, for instance, the approaches like reinforcement learning, in which, in a sense, you have artificial intelligence that is playing against the billions of possible pandemics, learn how, depending on what they see, is the best strategy with respect to certain objectives. So I think these are all projects that combines the mechanistic models, artificial intelligence, our knowledge of pandemics, and can put us in a way to have a much more timely response in case of an emergency.
Those are great problems. One last quick question, and I can't pass the opportunity talking to somebody like you who's at the intersection of so many exciting fields. What advice would you give to young researchers who are interested in pursuing an interdisciplinary career at the crossroads of network science and AI?
That's a good question. I think for sure is that I don't care how to say what is the trajectory in terms of preparing for that work, but I think strong foundation in mathematics, computer science, and statistics are crucial. You need to have that skills, how to say, up front and center, because that will be in the language, it will be in the daily use. Be curious, be open-minded. That's the other thing. So perhaps find your obsession. So the problem that really obsesses you, that you want to provide your contribution, but then keep reading and keep, how to say, venturing in other areas, because there is from that curiosity and that, how to say, explorations that you will bring always new material to solve your obsession, and then talk to others, always trying to bridge the communication gap. In many cases it's easy to say I'm a physicist, physicists are the best one, they can solve any problems, or I'm a computer scientist, well, I don't need anyone else, AI will solve all problems. It's never like that. Try to be a good listener before proposing your ideas, because that's again, for interdisciplinary work is crucial.
Great advice, and consistent with that vision of science being a team sport. Look, I am super excited about the potential of bringing network science to data. And we know AI is nothing without data today, at least that's the state of the art. But I think it's going to be a huge revolution for data science and for AI once we bring that network science and lay it on top of the super exponentially growing data sets that we have all over the place. Alex Vespignani, Sternberg Family Distinguished Professor and Director of the Network Science Institute at Northeastern University. Thank you for taking the time. Thank you for the words of wisdom. And thank you for joining us in this episode.
Thank you very much for having me. It was really a great pleasure. I look forward to all the excitement in artificial intelligence and network science. And, please join the force, so to say, we need the bright people and bright minds.
I think that the Network Science Institute has so much to offer the Institute for Experiential AI. So we look forward to it. Thank you, everyone, for listening. This brings a conclusion to another episode of our podcast, Legends of Data and AI, and see you in a future episode. Thanks, everyone.
Thanks for listening to Legends of Data and AI. We hope you enjoyed our deep dive into the world of data and AI. If you're keen to learn more about making data and AI work in the real world and in any organization, join us next episode and subscribe to the podcast. As always, you can head over to open-insights.com to sign up for our email list, learn more about the work we do, and have access to data resources. See you on the next podcast.